Hello everyone. The purpose of this lesson is to show you how to perform the batch export of ODB results. This lesson is quite straightforward. We'll follow our usual workflow. Let's start by creating one. First, let's build a model. For this model, we can set the thickness to, let's just set it to 200. This is a cuboid. Next, we assign it a density, a Young's modulus. And Poisson's ratio. We won't be covering complex physics here. It doesn't involve heat transfer, so let's just give it a thermal expansion coefficient. I'll just use this value for the coefficient for now. That should do it for now. Then assign the material to this cuboid and perform the assembly. Configure the analysis step settings. As for the analysis step, let's keep it as it is. Set the initial increment size to 0.1. Let's make this cuboid a little longer. Set its length to 500. Okay. Next, we will set up the loads for it. We won't be applying any concentrated forces. Instead, we'll apply constraints and then define a predefined field. For example, I'll set the temperature to 50 here. Then, let's create a new amplitude curve. Okay, that is also set up. Then, mesh the part into elements. This mesh is a bit too fine. The density is too high. Alright, the mesh is generated. Now, let's go ahead and create a set. Create a node set. We'll name it set1. We shouldn't define the set here. We put it in the wrong place. I should set it on the other side. Okay, next we will solve this job -1. Let's just name it job -1. Alright, as we can see here, the simulation is complete. Let's take a look at the results. Because we are simulating a thermal expansion process, this area is constrained, so there will definitely be stress. But we aren't focusing on stress right now, we're looking at displacement. As you can see in the negative z direction, a relatively large displacement has occurred. So what is our next objective? Our next goal is to extract this displacement data. Now, regarding writing a Python script to extract our displacement results, how should we go about it? First of all, as shown here, we should start by importing the necessary modules. The second step is to open our ODB file. The third step follows the hierarchy we discussed in the previous module. Navigating down level by level, first ODB, then steps, followed by frames, and finally, the field output. Next, we need to define a set variable. This refers to the node set set1 that we defined during assembly. We want to extract the data for set1. To get this displacement, we need to use the phi get subset phi command. Set the phi argument equal to this set. Essentially, it points to set1. Then we open a file named phi.txt. Assign it write permissions. Once the document is open, we assign the file object to the variable phi. Then use phi write to write data into the document. What are we writing? We'll write these 4 pieces of information: the node label, the displacement in the x direction, and the displacements in the y and the z directions. Next, we need to perform a traversal loop. And during each iteration of the loop, regarding this specific point here, specifically for this u phase set variable above, we need to access its values and iterate through them. So what do these values contain? We can take this object, import it directly, and then we can examine its data structure. We can use the prettyprint command we mentioned earlier. There is a slight issue here. Let's just use the standard print function instead. As you can see, what components does it contain inside? You can see that it includes things like labels, right? Then the descriptions, some names, types, and then these are our values. So if we want to export these values, then we need to be right here and iterate over these values. Then we can look further into what exactly is contained within these values. We can see that the nested structure of these values consists of a series of objects These objects actually represent the individual nodes in our set. Now, for these nodes within the set, what we need to do is extract the specific data for each node. Let's break it down further. Let's drill down into the data structure. As we can see inside here, there are quite a few of these objects. Mainly, we have the data attribute. This data attribute is where our displacement results are actually stored. It is the specific location for the displacement values. So, if we want to extract this displacement, we should iterate through U phase set values. This is essentially equivalent to all the node objects within the set mentioned above. Then, from each node object, we retrieve the node label and the node data, where data 0 is the x direction, data 1 is the y direction, and data 2 is z direction. Actually, there are other types of data available here as well. For example, regarding the Mises stress, the value here is none. This is because when we were defining the field output earlier, we didn't request to extract the Mises stress at all. The only thing we extracted was U displacement. Consequently, the minimum principal stress is also unavailable. As for the maximum principal stresses and many other data points, they are not available either. The only parameter that contains data is this displacement value. Now, once we have extracted the data, we need to write it to a file. How do we do that? First, we assign the data to a variable and then write it out using this variable, specifically using the write command. When we handle this variable, since we want to output it in a string format, we must use formatted output here. The purpose of formatting is to output the actual values stored in the variable. Those placeholders represent variables, not the literal characters we want to print. In other words, in this part of the script, it shouldn't output these curly braces themselves. Instead, it should output the values that they represent. And what it represents is actually the node label along with the values in the x, y, and z directions. Finally, we close this utxt file. Close the ODB as well. Right, that is our script file. Now, let's go ahead and run it. As you can see here, a utxt file has been generated in this directory. It contains our data, but we can see here the values are all to the power of -33, which indicates something is wrong. Most likely, we have selected the wrong nodes or the wrong set in this part. As you can see, we have obtained this result in this section here. Now, let's make some modifications to it, because we previously set the point at the constraint position. So let's change it now and run the simulation again. Okay, the simulation run is complete. Now, let's execute the script again. Let's open the file again. You can see that the values are different now. The first column on the left represents our node labels. The second column is the x direction displacement. The third column is the y direction displacement. And the fourth column is the z direction displacement. We can see that displacement in the z direction is the largest, and they are all negative. The maximum negative magnitude. That is because after we apply the constraints, it undergoes expansion. During the process of thermal expansion, it will naturally expand along the z-axis. And these expansion displacements will accumulate. On the other end of the model, the z-direction displacement will definitely be more pronounced. Now, regarding the batch extraction of this data. When it comes to extracting results, we are not limited to just extracting displacement. We can also extract stress values. That is also possible. This works perfectly fine. You can try extracting those on your own. There is one more thing to note. We initially use job-1 as the file name here. To make the script more robust and complete, we should specify the full file path. The full path can be written like this. You can format it this way. That covers the main content for this lesson. Thank you, everyone.
Focus on various issues in finite element analysis. For more related professional knowledge, please follow my YouTube channel or click on the relevant links of each video to learn.